Our next topic is resting membrane potential. So what is resting membrane potential? Well, if you look at living cells, all the living cells in your body, you got the nucleus, you got the DNA, you got the different proteins, sodium-potassium pump over there, okay, plus pump. Now, I want you to know one thing. If you were to take a voltmeter with those cathode ray oscilloscope displays located over there, and you put a little micro electrode inside the cell and one on the outside of the cell. This little voltmeter is going to measure the potential difference across the membrane. And so what it does is it's going to tell you the what's the amount of charge that's sort of separated, giving rise to voltage, meaning potential difference across the membrane. And this will be the inside value when you compare it to the outside value. So what does that mean? If you took these microelectrodes, put one inside the cell and one outside the cell, you will get a value mostly of minus 90 millivolts. That is to say that most of your living cells, the inside of the living cells is minus 90 millivolts compared to the outside. So you could say that the outside would be 0, for example, but then the inside is minus 90 millivolts. So there is this potential difference that exists across the cell membrane. And why is that? Well, because if you look at the cell membrane, first of all, that is like a capacitor made of phospholipid bilayer. The little phospholipid bilayers don't allow ions to go through it. Ions have a charge. Phospholipids don't like charged particles, at least they don't allow them to cross through. Then the other thing is you have the sodium-potassium ATPase pump that throws sodiums out and potassiums in, and you have many other different ion channels and carriers that are working in different scenarios. But eventually what happens is, in this cell which is resting, not firing an action potential, not doing anything, just living and existing and doing the bare necessities of life, you will find that the voltage across the membrane is usually minus 90 millivolts. This is because there is a difference in the concentration of various cations and anions outside the cell compared to inside the cell. Now, this causes a separation of charge. When you separate charge across a capacitor, it sort of makes a potential difference to exist. I mean, this is in simple terms. I'm sure many physicists, if they're watching this, would say I'm butchering physics, but it's good enough to understand the concept. You separate the charges, you make a difference in the concentration of various cations and anions across the membrane, and what you are going to end up with is a little bit of a potential difference that exists. So how does this happen? Why is the cell minus 90 millivolts in most cells? And be aware that when you look at many of your physiology books, sometimes they would give you the value of minus 70 millivolts in the neuron. Well, that is not for humans. That is for the giant squid. Giant squid, also known as the loligo. Or if you watch Pirates of the Caribbean, the kraken. But don't write that in your exam. Don't use the word kraken. But the point is, the giant squid was a wonderful animal with very big neurons, which when they were captured by those physiologists like Hodgkin, Huxley, and they were able to get these very large neurons in which they could put their little electrodes inside the cell and outside the cell very easily. So they would use these glass micro electrodes that could go into the cell without damaging it too much, because those cells were like around 0.5 millimeter to 1 millimeter thick. This was a very easy thing to study compared to human neurons, which are just microns in diameter. So having something that's almost a millimeter thick, at least 0.5 millimeter to 1 millimeter thick, allowed people to study it. And in the squid, they had different gradients, different ion channels, different composition of body tissues, and even of the different transporters. So the minus 70 millivolts pertains to the giant squid value. But if you read Books like Guyton, it will say minus 90 millivolts in the human. So please don't mix this up. Many people, including many teachers, will not be able to tell this difference most of the time. Are there other cells with different RMP values? Definitely. Your hair cells in the ear, the inner hair cells that pick up the vibrations and transduce sound, they have around minus 60, minus 70 millivolts. The pacemaker cells have it around minus 60 also. So there are exceptions. Everything in physiology has exceptions. You could almost say something's a hard and fast rule, but then there's always an exception that comes. The body never ceases to amaze you, so you always keep learning. But I want you to realize that there is an RMP value of minus 90 millivolts, and we are going to discuss how this happens and why this occurs in human beings. So how does the resting membrane potential exist? Let's get to it. Now, let's look at a cell. And cells have got DNA. DNA makes proteins. Through transcription and translation, you get different proteins. So let's talk about the first thing that happens over here. Number one thing that contributes to resting membrane potential, and which is the least important contributor, is the fact that you have some molecules called mRNA and various different proteins which have negative charge on them. So this mRNA and protein which exists in the cell and not outside the cell makes the cell on the inside a little negative. So it contributes to that minus 90 millivolts in such a small quantity that we are just giving it an honorary position over here. So the negative charged big molecules, macromolecules, like such as your proteins, different amino acids, and your RNA, and all these other big proteins. Next, we have the other thing. Sodium-potassium ATPase pump. Again, DNA makes RNA that makes sodium-potassium ATPase pump. What does that do? That throws 3 sodiums outside and takes 2 potassiums inside. Now, you must remember that 3 sodiums are going out. 3 cations with their positive charge are going out, and only 2 cations with the same amount of charge, meaning monovalent cations, are coming in. So that means 3 positives are going out, 2 positives are coming in. What are you doing? You're going into a sort of cation deficit because of the sodium-potassium ATPase pump. This sodium-potassium ATPase pump is going to create a little bit of negativity in the cell, but that again is negligible. Books like Guyton say they contribute to around minus 5 millivolts of negativity, but certain other books would argue and say no, it's much lesser than that. It's up to minus 1.5 millivolts. So depending on which book you use, let's just respect Guyton and say minus 5 millivolts, but in reality I would like to say that it is much lesser than that, its contribution. However, without sodium-potassium ATPase pump, we will not get that minus 90 millivolt value so easily. You see, the main function of sodium-potassium ATPase pump is that it will create gradients where there are more ions like sodium on the outside, 140 milliequivalents on the outside, compared to the inside sodium value of only 14. And the potassium value on the outside is 4 milliequivalents, while the potassium on the inside is 140. Now, you must remember these values till you die. Sodium value, potassium value outside in the ECF and inside in the ICF. Never forget these values. The gradient created by the sodium-potassium ATPase pump gives rise to the next step, which plays a big role in resting membrane potential, which is